Ladies and gentlemen, welcome to another installment of the Research Solutions lecture series. Today, we embark on a journey to explore the intricate topic of understanding the impact of heavy metals on plant physiology and strategies for mitigation. Agriculture, the bedrock of our existence, provides sustenance, energy, and resources. However, it doesn't come without repercussions. In this lecture, we'll meticulously dissect how heavy metals in agriculture mold our environment and delve into strategies to temper their impact on plant physiology and mitigate their ecological footprint. Now let's start our lecture. We divided our lecture into two sections. Section A: Effects of heavy metals on plant physiology. Included 1. Reduced growth, 2. Toxicity, 3. Nutrient imbalance, 4. Water uptake and transport, 5. Chlorosis and necrosis, 6. Reduced yield, 7. Contamination of edible parts. Section B: Mitigation strategies for heavy metal impact. 1. Phytoremediation, 2. Soil amendments, 3. Soil testing and monitoring, 4. Crop rotation and soil management. Let's discuss first. Introduction. Heavy metals are metallic elements characterized by high density and potential toxicity, naturally occurring in the Earth's crust. Natural occurrence. Heavy metals exist naturally in the Earth's crust, with examples like lead, mercury, and cadmium found in varying concentrations. Anthropogenic contributions. Human activities such as mining, industrial processes, and agriculture significantly contribute to the increased presence of heavy metals in the environment. In Section A: Effects of heavy metals on plant physiology. 1. Reduced growth. Disrupted physiological processes. Heavy metals disrupt photosynthesis, nutrient absorption, and enzyme activities. Hindered photosynthesis. Interference leads to reduced ability to harness energy from sunlight. Impaired nutrient absorption. Heavy metals disrupt the plant's nutrient absorption capacity. Disturbed enzyme activities. Crucial enzyme activities are disrupted, affecting plant development. Stunted growth. Cumulative impact results in stunted growth. Developmental impairment. Overall hindrance in normal plant development due to heavy metal interference. 2. Toxicity. Reduced plant growth. Toxic threat at low concentrations. Even low concentrations of heavy metals pose a significant toxic threat. Oxidative stress induction. Accumulation of heavy metals triggers oxidative stress in plant cells. Cellular damage. Oxidative stress leads to cellular damage in plant tissues. Disruption of metabolic pathways. Heavy metal accumulation disrupts vital metabolic pathways in plants. Impact on plant health. The toxic effects compromise the overall health of the plant. Overall well-being impairment. Cumulative impact results in a decline in the overall well-being of the plant. 3. Nutrient imbalance. Heavy metals competition. Heavy metals, e.g., lead, cadmium, can compete with essential nutrients like calcium, magnesium, and potassium for uptake by plant roots. Nutrient imbalance impact. This competition can lead to reduced absorption of essential nutrients, affecting critical physiological processes in plants. Plant health impact. Nutrient imbalance can impede plant growth, weaken cell structure, and compromise overall health. Developmental implications. Hindered nutrient uptake can result in stunted growth, reduced yield, and increased susceptibility to diseases. Environmental concerns. Accumulation of heavy metals in plants may pose risks for human and animal consumption, highlighting the broader environmental implications. 4. Water uptake and transport. Cadmium interference. Cadmium disrupts water uptake and transport by interfering with the plant's root system. Cellular impact. Cadmium affects cell membranes, reducing their permeability and disrupting the flow of water into plant roots. Vascular system disruption. Cadmium can block xylem vessels, impeding the upward movement of water and essential nutrients within the plant. Stress response. Water stress due to cadmium interference triggers plant stress responses, leading to further physiological imbalances. Reduced nutrient transport. Hindered water transport limits the movement of nutrients, exacerbating nutrient deficiency and impacting overall plant health. 5. Chlorosis and necrosis. Visible symptoms. Heavy metal toxicity manifests as chlorosis, yellowing, and necrosis, tissue death, in plant leaves. Chlorosis explanation. Metals disrupt chlorophyll synthesis, leading to yellowing of leaves, reducing the plant's ability to carry out photosynthesis. Necrosis impact. Accumulation of metals in plant tissues causes cell death, leading to necrotic areas on leaves and overall tissue damage. Photosynthesis disruption. Chlorosis hinders photosynthesis, reducing the plant's capacity to produce energy and essential compounds. Hindrance to growth. Impaired photosynthesis and tissue damage from necrosis contribute to stunted growth, diminished yield, and compromised overall plant health. 6. Reduced yield. Cumulative impact. Inhibited growth, nutrient deficiencies, and physiological damage due to factors like heavy metal toxicity collectively contribute to reduced yield. Nutrient deficiencies. Hindered nutrient uptake and transport result in a lack of essential elements crucial for optimal crop development. Physiological damage. Chlorosis, necrosis, and other physiological disruptions directly impact the plant's ability to photosynthesize and reproduce. Significant yield reduction. The cumulative effects lead to a significant decrease in crop yield, posing economic and food security concerns in agriculture. Broader implications. Reduced yield not only affects farmers' incomes but also has implications for global food supply chains and overall food availability. 7. Contamination of edible parts. Metal accumulation in edibles. Heavy metals accumulate in edible plant parts, particularly fruits, vegetables, and grains. Health risks. Consumption of crops with elevated metal levels poses health risks for animals and humans due to the toxicity of these metals. Bioaccumulation dynamics. Plants absorb and accumulate metals, leading to higher concentrations in edible parts, especially in environments with elevated metal content. Monitoring importance. Regular monitoring of soil and crop metal levels is vital to detect and manage contamination, ensuring food safety. Risk mitigation measures. Implementing practices to reduce metal uptake, soil remediation, and regulatory actions are crucial for managing and mitigating the risks of heavy metal contamination in food crops. Let's discuss mitigation strategies for heavy metal impact. 1. Phytoremediation. Metal accumulation in plants. Certain plants can absorb and store heavy metals in their tissues. Phytoremediation process utilizes metal accumulating plants to extract contaminants from soil or water. Harvesting and disposal. After phytoremediation, harvested plants are safely disposed of, preventing re-release of metals. Environmental benefits. Phytoremediation is cost-effective, environmentally friendly, and suitable for areas where traditional methods may be impractical. Plant selection and monitoring. Successful phytoremediation requires careful selection of hyperaccumulating plants and ongoing monitoring of growth conditions. 2. Soil amendments. Soil amendments introduction. Lime, organic matter, and soil conditioners are added to improve soil quality. Alteration of soil properties. Amendments modify pH, organic content, and structure, reducing metal availability. Soil changes make heavy metals less accessible to plant roots. Lime for pH adjustment. Lime is used to adjust soil pH, creating less favorable conditions for metal uptake. Organic matter binding. Organic matter binds with heavy metals, limiting their mobility and uptake by plants, aiding in soil detoxification. 3. Soil testing and monitoring. Importance of soil testing. Crucial for assessing nutrient levels, pH, and heavy metal concentrations. Heavy metal assessment identifies heavy metal concentrations, allowing for proactive measures to reduce their impact on plant growth. Implementation of measures. Results guide actions like soil amendments or phytoremediation to mitigate heavy metal effects. Preventing plant stress. Timely interventions maintain optimal soil conditions, preventing stress, and promoting healthy plant growth. Sustainable agriculture. Essential for sustainable agriculture, ensuring efficient nutrient management and minimizing environmental impacts. For crop rotation and soil management. Crop rotation role. Alternating crops in sequence to optimize soil health and nutrient balance. Soil management practices. Techniques enhancing soil fertility, structure, and pH levels. Reducing heavy metal accumulation. Crop rotation and soil management mitigate heavy metal buildup. Diverse crop impact. Different crops have varying abilities to absorb and tolerate heavy metals. Improved soil health. Practices contribute to a healthier soil ecosystem. Minimized plant uptake. Soil management reduces the risk of heavy metal uptake by plants. Sustainable agriculture. Promotes long-term soil fertility, productivity, and environmental health. Conclusion. In conclusion, our exploration of the effects of heavy metals on plant physiology and mitigation strategies underscores the intricate relationship between agriculture and environmental sustainability. From the disruption of growth processes to the contamination of edible parts, heavy metals pose multifaceted challenges to both crop health and human well-being. The strategies discussed in Section B, such as phytoremediation, soil amendments, testing, and crop rotation, offer tangible approaches to address these challenges and pave the way for a more resilient and sustainable agricultural future. Future recommendations. Advanced remediation technologies. Invest in research for advanced phytoremediation technologies and soil amendments to enhance their efficiency in mitigating heavy metal impacts. Integrated monitoring systems. Develop integrated monitoring systems that combine soil testing, remote sensing, and data analytics for real-time assessment of heavy metal concentrations in agricultural landscapes. Public awareness and education. Launch comprehensive public awareness and education campaigns to inform farmers, policymakers, and the general public about the risks associated with heavy metals in agriculture and the importance of mitigation strategies. Policy frameworks for soil health. Advocate for the integration of soil health considerations, including heavy metal management, into agricultural policy frameworks to promote sustainable farming practices. Research on crop varieties. Conduct research to develop crop varieties with enhanced resistance or tolerance to heavy metal stress, contributing to reduced uptake and enhanced overall agricultural productivity. Collaborative initiatives. Foster collaborative initiatives among researchers, farmers, government agencies, and industry stakeholders to implement and scale up effective heavy metal mitigation strategies. Global cooperation for food safety. Encourage global cooperation and standards for heavy metal monitoring in food crops to ensure food safety and mitigate health risks associated with metal contamination. As we navigate the complexities of heavy metal impacts on agriculture, these future recommendations aim to propel us toward a more sustainable and resilient agricultural landscape. And so, as we conclude this enlightening journey into the realm of heavy metals' impact on plant physiology and the strategies for their mitigation in agriculture, let us reflect on the pivotal role each of us plays in shaping the future of our food systems. The challenges are significant, but so too are the solutions within our grasp. As stewards of the environment, farmers, researchers, policymakers, and individuals alike, we hold the power to implement and advocate for sustainable practices. Together, through continued innovation, awareness, and collaborative efforts, we can cultivate a future where agriculture thrives in harmony with nature, ensuring not only the abundance of our harvests but also the health of our planet and the well-being of generations to come. Thank you for joining us on this exploration. May your commitment to sustainable agriculture and environmental stewardship echo beyond this discussion, influencing positive change in the fields and landscapes we all share. Until we meet again on our next journey of discovery, stay inspired and continue sowing the seeds of a greener and more resilient tomorrow.